Now remember, if we have a Turing machine and we want to know if a string is accepted or not by this machine, we will write the input string on a tape and do the necessary transitions, at the same time showing how the tape will be changed over time. We say that we will simulate the machine on the given input. Now, at any moment of this work, we will look at the tape, see what is the content there, what is the string that is available there in the tape, on which element the tape head is pointing, and in which state we are in the machine, from which state we will be moving next. This information defines a configuration. So a configuration is the information about the content of the tape, the actual state and the transition diagram, and the position of the tape head at any moment of the computation. So here, for example, in this moment, the tape contains the string X, A, Y, B, B. The tape head is scanning or is reading this cell containing A, and the actual state is Q2. We may write this simply XA Q2A YBB. We remark here that we have this string written here, XA AYBB, and we will mention the state in which the machine is just before the symbol on which points the tape head. Now, if we apply the transition from that state, Q2, the transition says that if it's A, we will write the symbol A. The symbol A there will not be changed, and we will move left. So we'll apply this transition and see what will be the content of the tape and on which cell the tape head will point. We will write simply that the content of the tape will be X, A, Y, B, B. The next state will be Q2, since here it's a self loop. Q2 will be written just before the symbol on which the tape head is pointing. See here, the tape head is pointing on the first A here on the tape. So we'll write Q2 here before the symbol to know that the following transition will be made from Q2. According to this, given any input string, we can compute all the possible configurations. Starting from Q0, having the input symbols written on the tape, we will follow the allowed transitions according to the graph and write here what will be the content of the tape, and at any time we will mention what is the symbol pointed by the tape head, and here just for clarity we will mention what is the state from which we will advance next time. So the list of all possible configurations, starting from the initial configuration, this one, until the last configuration, which mentioned that we are in a Q accept or Q reject. The set of all of these configurations define a computation history. A computation history is the sequence of all configurations taken by the machine when running on a specific input. Okay? We may write this computation history simply by showing at any time the list of input with the state in which the machine is actually there and we will put this state just on the left of the symbol pointed by the tape head. This relation here is called yields. So the first configuration here yields to this configuration. This configuration yields to the next one. And we will look for all the possible yields until stopping, until finding that the machine halts with an accept or a reject. So for a given input, the machine will be simulated on this input. We will be writing all the possible configurations. If the last configuration is obtained and in which there is a Q accept or a Q reject, this defines a computation. So in short, a computation is the list of all the possible configurations that stops or halts, that reaches a Q accept or Q reject. If the computation reaches Q accept, we'll say that this computation is successful. If not, if it reaches Q reject, we will say that this computation is unsuccessful. Until now, we saw examples on which Turing machines halt, either with accept or reject decision. But in general, since we have the possibility to go on the tape either right or left, the machine may loop forever. We may not have the possibility to enter in a Q accept or a Q reject. So we'll say that the machine may have three possible outputs. May halt and accept the input when it enters the Q accept. It may halt and reject if it enters a Q reject, and it may loop forever without being able to enter an accept state or a reject state. Let's take this example to show these three types of results from a Turing machine. We have this machine. For example, if we take this input AAA, BCC, we'll compute the configurations and see if we enter a Q accept or a Q reject or not. So here the first time we will write this input on the tape, and Q0 here will be written on the left of the first symbol, since this is the symbol on which the tape head points. So from Q0, we see here A. We will move to Q1. So we will write here the state Q1. A will not be changed, so we'll write also on the same cell the symbol A. All the other symbols are not changed, so we will write AABCC. And here the state Q1 will be written just before the symbol A, because we mentioned here that we will move right. So we will be pointing on the second cell on the tape. So we defined the first yield. We will define the other yields until finding if we stop or not. We remark here that when we are in Q1 and we see the symbol A on the tape, we will move right. So the next configuration will be this one. We will move right. So we will point on the symbol B here. So we will have this configuration. From this configuration, we are in Q1 also, and we see a B in the tape. So we will move left. So the next configuration will be this one, AAQ1, ABCC. Here it's the same configuration as before. It's this configuration. So we will be in the same situation than before, and we will apply the next yields, and we will obtain AAQ1BCC, which is this configuration. So we remark here that the next yields will yield to the same configuration that we saw before, and of course this yield will be equivalent to the yield we've done before, and we will obtain again AAAQ1 BCC. And we'll notice here that we have a loop. We will have the same pattern again and again and again. So the machine will loop forever here without having the possibility to reach a Q accept or a Q reject. With the same machine, if we consider this input AAACC, we will look for the possible yields here. We will be able to modify the tape, advancing with the states of the machine, and we will find here that we will enter a Q accept. The last configuration here is AAACC Q accept. So the machine here will halt directly, will stop, and enter the result that this input AAACC is accepted. Let's take the string BBC here, write it on the tape, start with Q0, we see a B on the tape, we will take this transition. It shows that we will write a C in the place of the B, and we will move right. Move right here shows that we will be pointing on the second symbol of the tape, which is B. And the next state is Q2. So we wrote here Q2. Now from Q2, if we see a B, we don't have any transition. Here we have C, here we have blank. So this transition with B should lead to a reject state. So we know here that the input BBC is rejected. Now, if we focus on all the strings that are accepted by this machine, all the strings for which when the machine is simulated, it will enter an accept state, we will be defining the language of the machine. So the language of the machine is the set of all accepted strings, all the strings that lead to an accept state when simulated with the Turing machine. If we take, for example, AC, we see here that from Q0 with A, we will move right on the tape and advance here to Q1. From Q1, for this C, we will be able to go to Q2. And since here the string is finished with a blank, we will enter an accept state. So AC will be accepted. Also, if we have multiple A's here, from Q0 to Q1 with the first A, with all the other A's, we will stay on Q1. Then if we see a symbol C, we will go to Q2. And if the string has finished, we will move to Q accept. If we have a list of A's, one A here and multiple A's here, and then if we have one C or more, we can accept multiple C's here after the first C. This will lead also to Q accept. But if the string will start with a symbol B, there should be one B, only one B. After that B, a blank will lead to a Q accept. Or after this B, a list of C's also will be accepted. So a string in the form B followed by 0 or more C's will be accepted. On the other hand, if we start with B, then we find multiple C's and then we find another B again here. There is no transition with B. This should lead to a Q reject. Also, double B will not be accepted. The first B, then one A, it won't be accepted. Also, one B, multiple C's, and then one symbol A won't be accepted. Here, with the same manner, we may look for the strings that are not accepted, either by entering explicitly in a Q reject or by looping. We saw here the strings in which we start with A and then we have a B. We loop forever and we will not be able to reach a Q accept. So these will not be members of the language of the Turing machine. After discussing more examples, we may write that the language of this machine will be all the strings in the form 1b followed by 0 or more c, from here 1b followed by 0 or more c's, or if we take this direction we will accept 1a followed by more a's. For this we wrote here a plus. Then we have to find 1c, and this may be followed by more c's. For this we wrote here c plus. So all the strings in this form will be accepted by this Turing machine. So this defines the language of this Turing machine. Now in general, the language of a Turing machine is the set of all the strings W in sigma star, such as the machine accepts W. So for all strings W that are members of the language, the machine M will accept these strings. When simulated on each of these strings, the machine will reach an accept state. And for all the strings that are not members of the language, the machine will reject these strings. Here the machine will reject explicitly by entering Q reject or by looping. We will say here, if the machine will loop forever, we will say that the machine rejects the string by looping. We'll say here that a language is recognizable if it is the language of some Turing machine. And this machine M is called recognizer for the language. By recognizer here we mean that the machine will accept all the strings that are members of the language. In fact, we have three possible classes for the languages that are designed by Turing machines. The language is called decidable if the Turing machine holds for each input. For the members of the language, we will be able to reach accept state, and for the strings that are not members of the language, we will be able to reach a reject state. Explicitly, the machine will enter a reject state. So here we will say that the language is decidable. But if the machine will enter an accept state, it will halt and accept if the string is accepted, but it may loop or halt and reject if the string is rejected. In this case, we will say that the language is recognizable or Turing recognizable. Okay, one may wonder if there are languages that are not even Turing recognizable. The answer is yes. In fact, if we have a Turing machine for this language that may halt or loop for accepted strings as well as for rejected strings. This means that for some accepted strings, the Turing machine is able to enter an accept state, and for other accepted strings, the machine will loop forever and won't be able to reach an accept state. And same for rejected strings. Some rejected strings on which the machine will enter the reject state, and for some other rejected strings, the machine will loop forever. In this case, we will say that this language is not recognizable, is not Turing recognizable.